Test, test. Can you guys hear me? Hello, hello? Can you guys hear me? Okay, test, test. Test, test. Can you guys hear me? Hello, hello? Okay, perfect. So let's get started. Give me 1 sec. I see the big echo here. I'm gonna try to share the sound one more time. Test, test. Give me 1 sec. There's a very big echo here. Mhm. Close. Close. Hello, hello? You can still hear the echo? Now it's good, right? Okay, perfect. All right, so let's get started. So welcome to our 2024 AMC10 AIME Bootcamp. So my name is Alex. So this is Alex Ivy School. We're actually providing the coaching services for North American math competitions, including but not limited to AMC, AIME, Euclid, all those kind of American and Canadian math competitions. And today we're going to focus on the 2024 AMC10 and AIME Bootcamp. We know that the 2024 AIME is pretty much around the corner. So in this lecture, we're trying to provide like 10 lectures, using these 10 lectures to cover the most important concepts for the upcoming AMC10 math competition. Generally speaking, the AMC10 math competition covers 4 major areas: the geometry, algebra, counting and probability, and number theory. So that being said, for our lecture, we're going to organize our concepts, try to cover as much as possible for these 4 major areas. We have 10 lectures in total. And for these 10 lectures, this is how we organize our lectures. So for each lecture, we're going to start with the concepts. I think the concepts are very important. We do not really just go for the practice, go for the questions one by one. But before that, we like to give you guys some short and brief explanations and summaries about the most important concepts that you will be seeing during the AMC10 math competition. And then after the concepts, we're going to do a quick summary. We like to show you guys what are the most important type of questions you will be seeing in the math competition. There might be millions of questions, but it's very important for us to summarize them, classical, and or should I say, just try to categorize them, classify them into several categories, and then we'll be able to find out the representative for each category, teach you guys the solution strategy that will be much faster than us just go for different exams, go for different problems one after another. So this is actually a very important part. And the third part will be the sample problems. Okay. So after we have the concepts, after we know all the summaries, the categories, the last step is trying to go for the problems. We're going to try to use the concepts and some strategies we introduced in the first 2 parts and try to solve them by using the real problems. So, because this is like a bootcamp lecture, I assume you guys already have some basic concepts for the AMC. So for the problem part, we actually focus on something relatively difficult. We focus on question number 21 to question number 25. Relatively difficult problem. Well, we have another lecture, which is our preparation course. In that preparation course, we do every day, we will give you some real problems, help you guys to do some practice, and then we're going to release the answer, and then we're going to see your problems, doing the reviewing back and forth. So in the crash course, we actually try to give you question roughly number 14 to number 20. So that being said, if you go to these 2 courses together, in our bootcamp lectures, these are considered to be some difficult, challenging problems. We're going to focus on the last 5 problems. Well, in the crash course, we're going to focus on some mid problems, right? From 14, 13, all the way to number 20. So these problems, putting them together is going to give you a very overall understanding about the most important concepts, most important type of problems for the AMC. For the first 10 problems from question 1 to question 10, they are fairly easy. You can do it by yourselves, right? So I think by using these 3 different parts together, we will be able to cover as much as possible for the AMC math competitions. All right? So if all good, we can actually jump to our today's lecture. This is our lecture number 1. In this lecture number 1, we're going to focus on 2D geometry. Okay, we're going to use 3 lectures talking about geometry. First lecture is 2D geometry. Second is the 3D geometry, or we say the solid geometry. And the last one will be the coordinate geometry. Okay, so let's jump to our first part. So the first part will be our concepts. What are the most important concepts that you need to know for the 2D geometry parts whenever you go to the math competition? Well, the first one, I think that's the most straightforward one, is the triangle inequalities, right? As long as you got a triangle, the triangle has 3 sizes, there will be a relationship between the 3 sizes, right? A plus B greater than C, B plus C greater than A, C plus A greater than B. This is like so easy peasy stuff. Actually, if you can recall what you mentioned, what you learned during our day school, the teacher might also mention that, okay, there are 2 things you have to follow. Any size, we add them together, the sum of any 2 sides will be greater than the third one. And also the difference between any 2 sides will be lesser than the third one, right? B minus C lesser than A, C minus A lesser than B. This is quite understandable. So that being said, you can actually have 6 different inequalities, right? But while you're in the math competition, if you really have to use such a property, do you really have to figure out 6 different inequalities? That's too much, right? Actually, a quick observation can find out all those subtraction related inequalities, they can be easily converted into the addition related inequality, right? So for instance, this guy is actually A lesser than B plus C. This is exactly this guy. So that being said, even though you have 6 inequalities in total, but you don't really have to remember all of them. You just have to remember all the sum related inequalities, right? And you know what? One step forward, there are 3 different equations, 3 different inequalities for the sum. Do you have to write them all? Or you just have to write something more important? So then let me ask you a question. Do you think in a real math competition, when the question asks you to write out all those inequalities, okay, you write out all those sum related inequalities, or it doesn't matter? You can just maybe write 1 or write 2 rather than 3. Who knows that? Okay. Actually, the answer is no, not necessarily. As long as you can find out the sum of 2 relatively smaller size is greater than the biggest size side, and then this will be good enough. Whenever you have 3 sizes, right, you do not have to randomly pick up 2, add them together greater than the third one. No, it's not really efficient. As long as you can find out the 2 relatively smaller size, adding them together, you want to make sure this is bigger than the third one, or we can say bigger than the biggest side. So this will be good enough. All right? So this is our actually the first part, triangle inequality. And the other one is also very intuitive, right? Whenever you have a triangle, the 3 angles, adding them together equals to 180 degrees. That's it, right? All right. So the first one, let's go to the second one, the Pythagorean theorem. Pythagorean theorem is actually something so important, and you're going to use it from time to time, right? Pythagorean theorem says as long as you have a right triangle, you have two sizes, then automatically you're going to have like a squared plus b squared equals to c squared. C is the hypotenuse. You know what? Actually, in the real math competition, the question barely really asks you to use the Pythagorean, do a calculation that give you two sides to the third one. It might happen, but from time to time, the question is going to ask you the other way around. That is, I give you a random triangle, and then I give you the three sides, okay? And then using your own calculation, you can find out the three sides actually meet such a Pythagorean relationship. So that being said means what? Means this is actually a right triangle. Is it right? So the question does not really give you this is a right triangle or not. You have to figure out this is a right triangle by calculating the Pythagorean relationship. So that being said means what? You need to remember, okay, if I give you three sizes, without really digging into the heavy calculation, you just have to remember, okay, the three sizes automatically form a Pythagorean triple, right? A Pythagorean triple. So I have actually listed out several Pythagorean triples. These are very common ones. You're going to see that from time to time. And especially I want to highlight these pairs because these were tested in the AMC. In the history of the AMC math, they actually give you some problems like this. In a problem, maybe the question directly give you the three sizes. Maybe you have to do some calculation to figure out the three sizes. But no matter what, you will find out the triangles with the following three sizes. And you'll be able to find, okay, this is actually what? This is actually a right triangle. Okay, this is actually something very important. Okay, the next one you need to remember is the angle bisector theorem. You know, angle bisector, let's say I have a triangle here and AD is the angle bisector. Of course, you have these two angles are the same, right? But trust me, from the AMC's perspective, they barely test you this. You have a triangle, you have an angle bisector, okay, two angles are the same, so what, right? Well, the most important thing is that as long as you have an angle bisector, you will automatically have such a angle bisector theorem. It actually gives you a side relationship from the angle bisector. So what is that? Let's check it out. BD over CD actually equals to AB over AC. So basically, angle bisector, this is actually an angle relationship, right? It gives you like two angles are the same. However, from such an angle bisector, you not only have the angle relationship, but also have the side relationship. Just like I said, the side relationship is actually way more important than the angle relationship because you can use the side relationship to generate some proportional relationship for different sizes, right? And then taking from there, you might use some side manipulation and then do some flowery or complicated calculation. So trust me, this is way more important than just two angles are the same. If you go back to the math competition, the AMC math competition, I'll say 50% is actually using angle, like the angles are the same. 50% is actually using the side relationship. However, if you go for last 5 years, almost 90% of the problems, as long as it gives you the angle bisector, it just tests you the side relationship rather than the angle relationship. Bear in mind, this is actually something very important. All right? Yeah, if you have any question, just let me know. I think we have the chat open. You can basically type your answer in, type your question into the group chat. And I'm actually monitoring the group chat all the time. I'll let you know whenever I see your questions. Okay? Let's go to section number 4, the centers of a triangle. Well, you know, as long as you have a triangle, you have multiple centers, right? You have the centroid. I'm going to change a different color. You have the centroid, which are 3 millionth intersection. You have the in-center. In-center is actually what? 3 angle bisectors intersection. You have the circumcircle. The circumcenter. Circumcenter is actually the 3 bisections intersection. And you have the ortho center. Ortho center is actually the 3 heights intersection. Right? And this is actually something very understandable. You know what? For all those 4 different centers, the most important one is actually the centroid, aka the 3 medians intersection. Why? Because there are so many interesting properties for this centroid. Okay, the first one, I think everyone knows that the centroid actually cut your 3 medians into 2-to-1 parts, right? This is 2-to-1. So this is 2-to-1. And this is 2-to-1. Why I use different color? Because for my my blue 2 and my green 2 and my black 2, they're not the same length. However, the blue to blue, the green to green, the black to black, the proportions are the same, 2-to-1 relationship, right? The 3 medians are not the same for sure, but they were all cut into 2-to-1 relationship. Second, you know what? This guy is what we call a mass center. It means what? The gravity of this triangle, that's actually the center. That being said, if you actually use your finger, you can actually, if you use your finger to poke on that point, you can actually make it this triangle balanced on your finger. So that's actually the mass center, the gravity focus on the center. And then from the coordinated geometry perspective, let's say if we have these 3 coordinates, x1, y1, x2, y2, x3, y3, okay? When we have the 3 coordinates with different 3 vertices with different coordinates, and then you will be able to find out what is the coordinate of the centroid, which is actually the average for the 3x value and the average for 3 y values. That's it. It's a very straightforward way for you to determine the coordinate of a centroid. All right, so these are very easy piece of stuff. So let's continue. Our lecture, we just want to use a very short time to give you guys overall summary without jumping into something super in detail. Okay, congruency. Congruency and similarities, they are twin brother. They're the most important thing for the 2D geometry. So let's get started with the congruency. How to determine 2 triangles that are congruent to each other, right? Congruent means they're exactly the same length, the same angle measurement. So the first one is actually 3 sizes. If 3 sizes are correspondingly the same, of course, 2 triangles are congruent to each other. Or SAS, side, angle, side. 2 sizes and their included angles are the same. Of course, 2 triangles are congruent to each other. Angle, side, angle. 2 angles and their included side, right? Angle, angle, side. 2 angles and one is the opposite side of the angle. They're correspondingly the same. So 2 triangles will be congruent to each other. And especially for the right triangle, if you have a hypotenuse and you have a side, they're the same. Of course, 2 right triangles, they're automatically the same, right? Because you already have a right angle here. So either it goes to ASA or AAS. Either way, you can make sure 2 right triangles are congruent to each other. Well, the only thing I think people need to remember is that side-side angle, this is not a correct determination rule to see 2 triangles that are congruent to each other, right? Because you see, I can give you an example. I have 2 triangles. They both have here, the blue ones, they're 11. And they have this green angle equals to 30 degrees. And what about this? I have the other one is 60. It's like 6 in terms of measurement, 6. However, you can actually create 2 triangles that are facing the same condition. One is a triangle here or a triangle here, right? So of course, you know, these 2 triangles are not the same. One is actually acute triangle. One is like obtuse triangle. right? So that being said, you won't be able to find out two exactly same triangles using the SSA, right? This is not an effective determination rule. Well, why I'm saying this, I just want to give an example saying that, you know what? Even though SSA is not a correct determination rule, but it actually means what? It means there are two triangles can be formed, right? The green one and also the blue one, right? Maybe we'll change color to red, the red one, right? So that being said, you might have two candidates that they're actually meeting the same condition. However, we know that for the green one, definitely it is congruent to the left triangle. It's only like the black one or like what is called like the red one doesn't make sense. However, in the real exam, if you can determine one triangle is obtuse, another triangle is acute, right? So for instance, in this problem, you can find out, okay, the acute two triangles are definitely congruent to each other, but it's only the obtuse triangle does not make sense. So I'm just saying, if you can rule out the obtuse triangle possibility, then you can say that those two remaining acute triangle, they're still congruent to each other. You guys follow me? So even though we say this rule is not correct, but there are some conditions. We mentioned that, right? If you can find, like the only reason they're not good is because you might have two shapes. One is acute, one is obtuse. But if for some reason you can definitely rule out, this is not going to happen for have an obtuse triangle, for instance. So that being said, you will be able to determine the remaining one could be always congruent. This is what we introduced in our regular lecture. So you need to say, right? This is not always no. There are some conditions for that. Okay. Yeah, before we jump to the similarity, you can find out for all the congruency related rules, at least you have a side condition, right? You can have one side, two sides, three sides, I don't care, but at least you need to have a side condition. Okay? Now let's go to similarity. Well, similarity is actually more casual compared to the congruency, right? So how to say two triangles that are similar to each other, as long as you have, change color, two angles that are the same, because the total sum will be 180, the third one will be automatically the same. Or two sides that are proportional to each other, while the included angles are the same. Or you have three sizes, right? Or you have three sizes. So these will make sure two triangles are congruent to each other. Well, people will keep saying, hey, Alex, what about the other, if I do comparison between the congruency and the similarity, I should have the ASA and AAS, right? And this is what I got from the congruency. How come I do not have it here in the similarity? Well, the answer is that similarity is more casual. As long as you have two A's, it's going to automatically jump to the first category, right? You have two angles are the same. There's no need to worry about the size. Or you can have three sizes or two sizes with an included angle, but both correct. This is actually something very important between the similarity and the congruency. All right, if all good, let's go to the law of sine and law of cosine. Sine law, cosine law, they're actually what? They're actually a twin brother, right? These twin brothers always help us to find out, okay, what it is, how are we going to do the comparison between the two, so on and so forth. So in terms of the sine law, these are the sine law, right? A over sine alpha, B sine beta, C sine gamma equals to R. What is this R? So do you guys know what is this R stands for? R is what? Okay, tell me. What is this R? R is actually the radius of the circumcircle, right? Radius of the circumcircle. right? The radius of the circumcircle is actually your r. Right? You guys should already learn that in your day school or like some other summer schools. So this is actually the sine law. And what about the cosine law? Cosine law goes like this, right? I'll take one as an example as a cosine A equals what? B squared C squared minus A squared 2BC, right? How to remember this? You can say you can never get what you want. You can never get what you want. Why? Because A, you're looking for A, right? So here is B plus C minus A. You won't have A, but you have to subtract A. And also talking about the denominator, there's only B and C. You never get what you want, right? So cosine A, there's no A on the right-hand side. Okay, after you get this, these are actually, trust me, these are actually something very important. You always want to use the sine law and cosine law, help you to build up some relationship between the size and the angle, right? And especially, I believe something more important is the cosine law, because cosine law is the only one law which brings the relationship between pure angles and the pure size. What I'm trying to say, like this, you see, on the right-hand side of the cosine law, you only see the side, right? There's no angles, only the side. While on the left-hand side of the cosine law, there's only angles. So that being said, the cosine law is actually a very powerful law. It actually convert the relationship between the size to the angles, right? It converts the relationship between the size and the angles. So this is actually something very important. So whenever the question gives you a bunch of side relationship, but end up asking you to do some angle relationship, cosine law is the most important stuff. Okay? And moving forward, there are some very easy peasy stuff I think you need to remember is talking about the quadrilaterals and the polygons, how to determine the area of trapezoid, top, bottom, height divided by 2, the area of like parallelogram, right? Which is like the height and also the bottom. And if I give you a polygon, I ask you to determine what is the total interior angle sum. It's going to be 180 times n minus 2, where n is what? N is the how many n-gongs, right? And the total number of diagonals in the n-gon is n times n minus 3 divided by 2, right? Do you guys know this? So if there is only, this is 4, like this is quadrilateral, there are 2, right? Whenever there's 5, there are 1, 2, 3, 4, 5, right? You can keep doing the math here and there. You'll be able to find out the number of diagonals in a given polygon. This is actually something very important. Okay. Moving forward, okay, let's try to go to the circle part, right? We pretty much finished all the triangles, quadrilaterals, blah, blah, blah. Let's go for the circles. What are the important concepts for the circles? First, area of a circle, pi r squared, the circumference of a circle, 2 pi r. These are something so easy, right? You know that from your elementary school. Okay, power of a point. This is actually something so important. We talk a lot in our regular lectures. So we actually spend like almost like 10 lectures, 20 lectures talking about all the 2D geometries, but now we have to consolidate everything into a very short lecture. So power of a point is actually a series of theorems. So it has like 3. One is the chord theorem. One is the tangent chord theorem. Tangent secant theorem. The last one will be the secant theorem. So what is a chord theorem? As long as you have 2 chords interacting with each other, within a circle, automatically you have here, right? D, EB equals to AE, C, right? The other part, whenever you see a tangent, whenever you see a secant, you have AB square, BC, BD, BC, BD, right? And the last one is CB, CA, CD, C, CB, CA, CD, C, right? As you can actually see that the difference between the tangent chord theorem and also the like the tangent secant theorem and the secant theorem are very similar. You see, whenever the chord is here, I'm going to give you this example. You see, at this moment, this is the secant, right? But as long as the secant going out, all the way it goes to here. So that being said, your secant is going to be degraded into a tangent. Does it make sense? Your secant will be degraded into a tangent. So that being said, your CB and your CA will become the same. It used to be 2 points, right? Degenerated into 1 point. So this is going to be CA square, CD, CE, right? CA square, CD, CE. So that being said, your tangent secant theorem and your secant theorem, they're generally talking about the same thing. Does it make sense? All right. If all good, let me ask you a very important question. In the math competition, especially in the 2D geometry area, from time to time, you're going to see a lot of like tangent. The question might give you some tangent conditions. Do you know what are your conditional react whenever you see the tangents? What you're going to do whenever you see the tangents? Who can tell me? As long as in the math competition, the question gives you a tangent relationship, what are you going to do? Somebody mentioned changes to sine, cosine. Change to, can you elaborate like a little bit? I don't quite understand. Change to sine, cosine? Ah, you mean no. Okay, I get it, Lucas. So you see okay, whenever you say tangent, you mean like the trigonometry tangent, right? The tangent convert to sine or cosine. But now we're talking about the tangent concept in the geometry. Tangent means there's a line tangent to a circle, right? This is not something you can change into sine, cosine. But your point is tangent alpha theta equals to sine theta cosine theta. But that's more from the trigonometry's perspective, but not from a geometry, right? Because in geometry, this is like a line tangent to a circle. Okay, no worries, nice try. The other students, do you know what, normally speaking, have you ever learned this? Normally speaking, whenever you see a tangent from auxiliary lines perspective, what are you going to do? Okay, maybe you don't really know this. Okay, I'm going to give you some summary. This is actually very important. Whenever you see tangent, as long as you see a tangent between the circle and the line, what you need to do is you can do a connection. Connect the circle center to the tangent foot. Because as long as you do this connection, you automatically have this perpendicular, right? This is understandable, right? A line, tangent to a circle, connect the circle center to the tangent foot, you will automatically have a 90 degrees. This is more for a line and a circle. Then what about you have two circles? If two circles are tangent to each other, you might have internal tangent, you might have external tangent, or you might have something like this. I'm going to give an example. Go like this, or go like this. Does it make sense? Right? Whenever you have like two circles that are tangent to each other, or maybe they're tangent to another line, you might end up with these three different scenarios. So the most important things goes like here. As long as you see two circles that are tangent to each other, in any circumstances, no matter what, you need to connect the two circle centers. In any circumstances, you need to connect these two circle centers. This is your step number 1. Connection. And then your step number 2 is, it really depends on different patterns. So for the first pattern, if you extend this circle centers connection to this tangent line, you will automatically have, let's say A1, A2, L. You have A1, A2 perpendicular to L. A1, A2 perpendicular to L. What about the second one? Same thing, right? Two circles that are externally tangent to each other. As long as you do the connection, A1, A2 perpendicular to L. Wow, what about the third one? The third one is actually, they are externally tangent, but we find out another common tangent line to this circle, right? In that case, you're actually using whatever we introduced here and here together. First, you're going to do connection between two circle centers. And because now you also have a line tangent to a circle, right? This line, L, is tangent to the circle. So you also want to do a connection between the two circle centers and L. Which makes sense, right? This is exactly what we mentioned in our number 1. And then afterwards, I'm going to show you something very important. Let's check it out. Let's check it out. Now you're looking at more like a trapezoid, right? This is your trapezoid. I'm going to do a perpendicular line from the smaller circle to the big circle. This is going to be 90 degrees all over the places. So here you're going to have what? The blue one is going to be a rectangle, right? Let's try to do some number crunching. If this is small r, this is big R, this is small r. So let's try to focus on this black triangle. Maybe I'll change it to red to make it more conspicuous. I'm going to drag it out, okay? I'm going to drag it out. Okay, so I know this part is big R minus small r, right? Because this is R. This is R. I'm going to change the color to yellow, make it easy. R, R. So this part is going to be here, big R minus small r. Makes sense, right? And then what about this guy? This guy is the connection between two circle centers. This is going to be big R plus small r. Is that right? This is 90 degrees. And using your Pythagorean theorem, this is going to be 2 under root big R small r. So that being said, your green part is 2 big R small r. Because you know your blue is what? Your blue region is what? It's actually rectangle. So therefore, this part is also big R small r. What is this part? This is exactly the length of your common tangent line, right? You have a common tangent line. They're tangent to these two circles. Of course, they intersect with these two circles. So the length is this guy is exactly 2 under root big R and small r. So trust me, this is what we call this guy is a magic right triangle. As long as you see two circles that are tangent to each other, always do the calculation. Most of the time, your calculation will be just focused within this magic triangle. Okay, Try to do all your calculations within this magic triangle, and you'll be able to solve a lot of problems. Do you guys follow me? Yes or no? Are we all good? Okay, felt good. Let's continue. Okay, the other part you need to know is the cyclic quadrilateral. As long as you have a circle, you'll be able to find a kind of like a quadrilateral inside, right? So this is actually something different for triangle. Let's say, as long as I give you a triangle, what kind of triangles, no matter what, you can definitely find a circumcircle for this triangle. So that being said, all the triangles, they must be cyclic. Means you can definitely find a circle which touches 3 like vertices within the triangle. However, it's not the case for a quadrilateral. Not all the quadrilaterals, if I give a weird quadrilateral, not all the quadrilaterals they can put into a circle. Means they can, maybe like the 4 sizes, like the 4 vertices, can be on the same circle. So it's only working for triangle. Not all the quadrilaterals, they are the cyclic quadrilateral. Okay, the cyclic quadrilateral. And how are we going to deal with that? Okay, how are we going to find out a certain quadrilateral is cyclic or not cyclic? The most important thing is there are several rules for you to determine a cyclic quadrilateral. So one of the rules is that, let's try to check these 2 angles. Whenever you have the opposite 2 angles, adding them together equals to 180 degrees, this is going to be what? A cyclic quadrilateral. Okay? As long as you have this 100 degree, this opposite 2 angles, adding them together equals to 180 degrees, this is going to be a cyclic quadrilateral. Okay? And also, as long as you have a cyclic quadrilateral, this is actually a very straightforward way for you to determine the area of this cyclic quadrilateral. Let's say you have a cyclic quadrilateral. This is A, B, C, D, 4 sizes. How you like to determine the area of this 4 sizes of this quadrilateral is going to be under root S minus A, S minus B, S minus C, and S minus D. Okay? So you don't really have to do something too complicated. You will be able to figure out how to get the area very quick. Okay? This is more like what? More like our Heron's formula, right? Heron's formula, what? When I have a triangle ABC, so I'm going to define the P equals to 2A plus B plus C, right? And S is going to be P, P minus A, P minus B, P minus C, right? You guys know this? The Heron's formula, right? So Heron's formula is actually quite similar to a cyclic quadrilaterals way how to do the presentation. So that being said, you would be able to always using the like an average of the 4 sizes or 3 sizes, whatever, and then multiply average minus A, minus B, minus C, minus D. That's it. This is actually a very expedited way for you to determine an area of a given quadrilateral. But this quadrilateral must be what? Cyclic, right? Actually, in our regular lectures, we introduce so many complicated properties, so many fancy ways how to determine a quadrilateral is cyclic or not. But due to the volume of our current bootcamp lectures, we can only give you the high-level things. But there are more than 10 ways how to determine, like, this is a cyclic quadrilateral. You can actually refer to our regular lectures about more details. But these are the most important things. The other one is the Ptolemy theorem, right? As long as you have a quadrilateral, it is cyclic, then you will have the Ptolemy theorem. Ptolemy theorem actually reveals the relationship between all the sizes plus the diagonals for a cyclic quadrilateral. So it goes like this. The product of your 2 diagonal, the product of your 2 diagonal equals to the sum of the product of the two opposite sides. AB, CD, there are two red ones. BC, AD, there are two green ones. So the two opposite sides, you multiply them together, and then adding them together is actually equals to the two diagonals product. And this is actually the famous Ptolemy theorem. And you know what? This is actually a necessary and a sufficient condition. It means what? As long as you have a cyclic quadrilateral, you will definitely have a Ptolemy relationship, right? However, if I just give you a random quadrilateral and it has a Ptolemy relationship, then you can claim this quadrilateral must be a cyclic quadrilateral. So that being said, this is back and forth, two directions, from left to right, from right to left. If it is quadrilateral, it is cyclic, this is going to have a Ptolemy relationship. And if you have a Ptolemy relationship, this is going to be a cyclic, back and forth. All right. So next part, I think this is also something very important. We want to give you guys a summary, how to determine the area of a triangle. So this is actually, I would say that most of the time, whenever the question asks you about any area, any kind of like area relationship things, you will be able to use 80% of the time, you will be able to solve the problem using all the formulas we introduced from here. So let's have a quick summary, how to determine the area of a triangle. First one is fairly easy using the definition. The bottom, the height, multiply them together, you get what you need. Second one is what I just mentioned, Heron's formula, right? Using the Heron's formula, if the question just gives you three sizes, no height, no nothing, you will be able to determine the area without talking with the height. The third one is actually using some trigonometry. Using the trigonometry goes like this. Let's say when I have like a triangle, this is A, this is B, and this is C. So how can I determine the area of my triangle? It's going to be A times B sine C. Means the product of two sizes and their included angle, right? The product of the sizes and their included angle. Which makes sense, right? Yeah, and also we can actually use these two things. I don't know if you guys are familiar with this or not, is using the in radian. What is that? In radian is the in circles radius. Let's say I have a triangle. This is my in circle. So the radius of the in circle times S. What is S? S is half of your A plus B plus C. Okay, I have a triangle. I have like three sizes, A, B, C. So the area of my triangle could be A plus B plus C divided by 2 and then times R. R is the radius of my in circle. Okay? Okay, this is one way. Whenever I give you in circle, we can also do the same thing as long as I give you a circumcircle. If this is triangle ABC, I have a I have A, B, C. Then how to determine the area of this triangle? The triangle's area is going to be ABC. Multiply them together, 4 times R. What does this R mean? R is the radius of the circumcircle. Okay, so that being said, if you have the radius of the in circle, the radius of the circumcircle, and the 3 sizes, there's no need for you to determine the height. You can directly determine the area of the triangle using such 3 conditions. Very important. Trust me, in a lot of AIME exams, they're using this solution right away. Yeah, later when I show you some AIME exams, if you go for the regular solution, they're extremely complicated. But if you know these 2 solutions, super fast. In our regular lectures, we already give the detailed proving for these 2 guys. So how to prove them? But for now, we do not have enough time. We're just going to skip it. But you can refer to our regular lectures. We're going to give you the detailed explanation how these two things they're actually being improved. Okay. And another thing I want to tell you, which is also very important, trust me, this guy, they test it every other year. Using similarity, they can also help you to determine the area. Because if two shapes, they are similar to each other, the area ratio would be the similarity ratios for fixed square. Do you guys know this? Yes or no? Can I have some feedbacks? If two shapes that are similar to each other, so the area ratio between these two shapes will be exactly the similarity ratios for a fixed square. Do you guys know that? This is actually something very important. And you know what? This one can be elaborated. The area ratio, if I change into the volume ratio will be actually the similarity ratios perfect cube. Okay? The area ratios perfect cube. So trust me, a lot of like complicated problems, trust me, if you do the regular way, that's going to take you forever. But if you know this similarities ratios perfect square equals to the area ratio, this is going to take, you know what, that's going to save you a significant amount of time. Okay? And some quick things I want to let you know. If I give you an equilateral triangle, the size of equilateral triangle equals to A, you need to determine the area, right? How to determine the area of the equilateral triangle? √3/4 A perfect square. This is actually something very, very important. Okay, so far, so good. I think these are very easy peasy stuff. So that being said, we actually completed all the basic concepts. You see, nothing really complicated. We just know everything already, right? Okay, so this actually finished our first part, the basic concepts. Now, let's go to our second part, some important types of questions. What you are looking at when you go to the AMC10, talking about the 2D geometry part. Generally speaking, I think there are four major big type of problems. The first one is area method. The question is going to ask you to determine the area of certain shapes. Sometimes you're going to use some definition. Sometimes you're going to use some flowery ways as we introduced previously. But generally speaking, the question is going to focus on the area. Second, later I'm going to give you sample questions. But first, I just like to list out all those all those big categories. The second one is actually, like I mentioned, similarities property. Similarity is actually a very important thing, right? Two similar triangles or two similar quadrilaterals, like whatever, all those similarity related properties are very important. And one of the most important thing is, just like I mentioned, the areas ratio is the similarity ratios for a fixed square. Areas ratio is the similarity ratios for a fixed square. This is actually one of the most important things. Sometimes you find out later, I'm going to give you an example. This is the AMC10 and AMC12, question number 25. This is exactly using this. Okay, AMC10, AMC12, they have some shared problems. And in this problem, it's actually shared. They're actually shared by these two, and they're both the question number 25. And if you use the similarity ratio equals to, like, similarity ratios perfect square equals area ratio, you solve the problem in 15 seconds. Okay, but if you go for the regular way, you're going to take maybe 20 hours. You're going to be 25 minutes go for the complicated way. So try to remember this. This is going to be very helpful. And the third one, I really want you to remember some angles trigonometry value. You know, we both know the trigonometry 30 degrees, 45 degrees, 60 degrees, 90 degrees, right? Everyone knows that. We don't know. We learned that from the elementary school. But this is not enough. If you want to be standing out for the AMC math, you want to expediently, extremely fast, significantly accelerate, you need to remember some special angles trigonometry value, like 15 degrees, 18 degrees, 36, 54, 72, 75. If you can remember the accurate value, I'm not asking the approximate value, no, the accurate value of these guys, sometimes you can save your time significantly. Trust me, I'm going to give you some examples. In our regular lectures, we really ask all my students to remember this, right? You have to remember this. If you do not remember, okay, so it's fine. You're going to take maybe 30 minutes to do the calculation, but you just do not have time. You have to give it up. But if you remember this, maybe 10 seconds, you figure out a question number 25, question number 22, very quick. I'll give you examples. You understand where we come from. And the last part is they're always going to ask you some circle, some tangent related problems. So these are the four major problems AMC love to test you from time to time. And we would like to give you guys a bit of like ideas for each of them. Again, our lecture is not just giving you problem, solution. It doesn't make sense. We need to give you the conditional react. So what are the common sense? Whenever you see such a problem, what are you going to do? Whenever you see another problem, what are you going to do? How are you going to use such a condition? How are you going to use another condition? This is extremely, extremely important. Our regular lectures keep talking about this every day. Now we just like, maybe we only have like very short bandwidth. We just give you highlight things. Okay, high level things. You're good to go. Are we all good? If all good, we can go to our section 3. Let's go to some real problems. Okay. Real problems. Okay, how are we going to deal with these real problems? Let's go to our question. Okay. So, like I said, there are 4 major categories, right? Let's go start with the first category, area. How we determine the area, sometimes using the definition, sometimes we use some flowery things, but we'll see. So let's go for our first problem. Okay. This is a problem that comes from 2023 AMC10A question number 24. Okay, this is the latest and greatest problem, right? Question number 24. So let's read the problem first. Okay, follow me whenever we read a problem. Let's try to highlight the most important things. 6 regular hexagon. Okay, this is important. Regular hexagon blocks a side length 1 unit are arranged inside a regular hexagon frame. Okay, you have a big regular hexagon frame and you have 6 little pieces inserted in the middle. Each block lies along the inside edge of the frame and is aligned with the other 2 blocks as shown in the figure. You see they're very tight, right? Squeezed very tight one after another. The distance from any corner of the frame to the nearest vertex of a block is 3/7 unit. I think this is important. The distance from any corner of the frame to the nearest vertex of a block is 3/7. It means what? This part. 3/7, right? The distance from any corner of the frame to the nearest vertex of a block is 3/7. Okay? Then what is the area of the region inside the frame which is not occupied by the blocks? So basically the question asking, what about like the white part? Let's have a look at it. How are we going to deal with this, right? I need to find out the area of the white part. The question give me is what? The big frame, the length is what? Oh, no. What is that? Oh, sorry. Like the smaller block is what, right? You see the question showing here. The side length 1 unit means, okay, this one is 1. This one is 1. Okay, if I want to determine the white area, so the area of the white is definitely what? The big hexagon area minus 6 times the small hexagon's area, right? This is quite understandable. The small hexagon is good because I already know the side is actually 1. So I will be able to determine it. But the most important thing is I need to determine the side length of the big hexagon. How can I determine the side length of the big hexagon? Let's have some quick look at it. And definitely I know this part is 3/7. This part is 1. I'm going to change a different color. 1. So my $1 million question is I need to figure out the length of this part, right? As long as I figure out the length of this part, my work is done. That's it. How am I going to deal with that? You see, this is not like, you see, my magic might happen here. I'm going to use this blue part, try to do all my magic, and figure out what is the length of the yellow part. But my blue part is not a regular shape. It's actually very kind of like a spoon or something, right? Of course, I won't be able to work with any irregular shape. I must convert it into a regular shape. Then I know what to do. How can I convert it into the regular shape and hopefully I can solve my problem? Who can tell me? How can I cut it into something regular and then I'll be able to fix my problem? Actually, there's a very easy way. Let's do a quick, let's do a very quick auxiliary line here and we'll be able to solve all the problems. I'll do a perpendicular line to the bottom. Okay, so that being said, as long as I do this, I'm actually blocking the upper part into a kind of like an isosceles trapezoid and the lower part into a like a parallelogram, right? So that being said, if this is 3/7, this is could also 3/7, right? 3/7 to here. And also, if this is 1, this is 1. And this is 1 as well. Oh, so that being said, you see, I already know this part is 1 as well. So the $1 million question is, as long as I can figure out the value of this part, my work is done. Is it right? You see, it reduced the complexity significantly. So the $1 million question is, how can I determine the value of this part? How can I determine the value of this part? If I could, okay, I solved the problem in no time. Well, to determine this part, I think I definitely need to work with the red trapezoid. My red little trapezoid has all the magics here, right? I'm just going to drag it out. My little red trapezoid, you're telling me this is 3/7, right? The top is 1, right? The top is actually one side of the little hexagon. This is 1. This is what? 60 degrees. With all those information, do you know how can I determine this? Is it easy? Is it easy? Anyone knows? Anyone knows that? I have a isosceles trapezoid. And in this isosceles trapezoid, you have the top, you have the bottom, right? And then how can you determine the side? Exactly. I see Zian. Zian has like the correct answer. Something quite easy. Let's check it out, right? This is something so easy. I'm gonna do some quick change. This is 3/7. This is 3/7. The remaining will be 4/7, but left and right will be identical. So this is going to be 2/7. This is going to be 2/7. Now, if I focus in this little triangle, this is what? This is a 60, 30, 90-degree triangle. So the hypotenuse will be twice of the 30-degree facing side. So this is twice 2/7, which is 4/7. Is that right? So this part is going to be 4/7. So easy, right? So therefore, the side of the big hexagon will be 3/7 plus 1 plus 4/7 plus 1. And the answer is going to be 3. Oh, now it's like so easy, right? We determine the side length. So I determine the side length of the big hexagon is actually 3. So now what you need to do is you just basically using this formula, right? The white part will be the big hexagon's area minus 6 small hexagon's area. How can I determine the hexagon's area if I just know the side? This is actually something so easy. If the side is A, you can do something like this. The hexagon can be broken into 6 small equilateral triangles. Is that right? So the area of hexagon is actually 6 area of the equilateral triangle. How can I determine the equilateral triangle's area? This is what we just mentioned previously. Still remember? Equilateral triangle's area is going to be what? 3 under 3a squared over 4. So therefore, this is going to be 6 over 4 a squared, which is 2, 3, which is 3 to 3, 2 a squared. You see, this is like so easy, right? As long as you know the side length of the equilateral triangle of this regular hexagon, you plug in into this formula, you'll be able to determine the total area. So what you have to do is so easy. You know this guy, a equals to 3. You know this guy, a equals to 1. Just plug in the value, you'll be able to find out C is the correct answer. You see, this is question number 24, right? But generally speaking, it's not really asking something too complicated, right? As long as you know the basic definition, how to determine the area, you're good to go. So far, so good? If all good, let's go for another problem. Okay? Our second problem is a problem that comes from, okay, I'm gonna click in here. This is a problem that comes from 2018 AMC10A, question number 24. Okay? So the problem says, let A, B, C, D, E, F be a regular hexagon. Okay, this is also a hexagon. You know, trust me, AMC loves to test your hexagon. In the older polygons, hexagon is the most important because there are so many special properties you can use here, you can use here. Try to remember it. Okay? I'm going to give you the graph, just trying to make our life easier. We have a regular hexagon. I'm give you the A, B, C, D, E, F, right? Okay, they have the side length equals to what? Okay, we denote X, Y, Z are the midpoint of AB, CD, and EF. Let's see. X is here. Y is CD. CD is here. And the Z is EF. Okay? X, Y, Z are the three sizes, are the three midpoints of AB, CD, EF, respectively. So what is the area of the convex hexagon whose interior is the intersection of the interior of ACE and XYZ? I have to figure out what is ACE. So the first one is ACE. Let me try to find out this equation. So let me try to find out this shape. ACE. Okay, AC is such a triangle. And XYZ. XYZ. Okay, ACE, XYZ. What is the intersection of this? This means what? You're trying to find out the area of this guy. Okay. This guy is not looking something so intersection here, here, here. Well, how can I determine the area of this guy? This might not be so easy, right? This guy looks like so irregular shape, right? How can I deal with this so irregular shape? Well, to deal with such an irregular shape, I think if you just really want to do it right away, I don't think it's like so easy. But think about it. All those hexagon problems, they can be actually using something like this. Try to break it into something as easy as possible. You know what? Let me give you a quick trick. I'm going to do a quick thing like this. It's going to really help you to simplify your calculation. You see, X, Y, Z already, they give you the three midpoints of the three sizes, right? I'm going to do the same thing for the remaining three. Okay? Okay, now I find out basically the midpoint of the remaining three sizes. So that being said, let's try to have a look at it. This blue region, and I think about like into this. This is actually nothing but my red region. My red region plus three blue triangles. Is it right? Red region plus three blue triangles. As long as I figure out this, my work is done. Right? My red region plus three blue triangles. As long as I figure this out, my part is done. But how can I make this out, right? This is actually something so important. Let's get started. Don't be worried. The internal one, like the red one, I think you already know what to do, right? We already talked about it. The red one, you can always go for, let me see here, line here. The red one, you can break it using sticks. 1, 2, 3, 4, 5 sticks. The red one is actually 6 equilateral triangles, right? So what about the 3 blue ones? The 3 blue ones is actually what? 1.5 right triangles. Is it right? Even though I'm using different colors, but you can see that. See, I'm going to give you an example. If you think this is one triangle, this is exactly the same as 1, 2, 3, 4, 5, 6, right? And for my blue one, it's actually only half of it. So that being said, my 3 blue triangles is actually 1.5 equilateral triangles. So that being said, the total solution will be 7.5 equilateral triangles. But how can I determine the equilateral triangle's area? Again, it goes to the same thing. As long as I know the side, I'll be able to determine the area. Is the side easy to determine? I'm going to use the color here. This is your side. Your side. This is your side. It means what? It's actually, let me try to do another thing here. Another thing here. Did you find out? This is your side. The side is actually 1/2 of the regular hexagon side. Does it make sense? The side is 1/2 of the regular hexagon's side. So with all those information, as long as you know the side, it's very easy for you to determine the area of the equilateral triangles. You'll be able to get all those information fairly quick. Does it make sense? So the answer will be 15, 32, root 3. 15, 32, root 3. Look, this is actually a so easy peasy process, and then you'll be able to use this to significantly expedite your calculation process. So far, so good? Are we all on the same page? Perfect. If all good, that actually wraps up our first category. Okay, using the area method, you'll be able to do a lot of calculations. Okay, if all good, let's go to our second category. Similarity properties. How can I use the similarity property help us solve some problem? This time, let me try to give you a relatively challenging problem. Let's go for an AIME problem. We'll see how we're going to use this to solve one of the AIME problem. This is a problem that comes from 2015 AIME question number 7. AIME question number 7 is roughly like the last 5 problems of AMC10. So let's have a look at it. How are we going to do? In the diagram below, ABCD is a square. Okay, so I have to highlight this. And point E is the mid. Okay, this is the mid of AD. Okay, point FG, they lie on CE, HJ lie on AB, BC, and FJ, FG, JH. FG, JH. I'm gonna highlight, use the color maybe red. This is what? This is a square. Okay, this is a square. If this is a square, okay, point KL lies on GH, MN, AB, AD respectively, so that KL, MN is also a square. KL, okay, like the red one and the green one, they're both two squares, right? The ABCD is a square, the big one is a square, and then you kind of like a tilt. You insert 2 squares, the red one and the green one. Okay, the area of the KLMN, this is 99. 99, okay. And what is the area of FGJH? Okay, I think the question is very understandable, right? You have two tilt squares. One is, the smaller one is 99, and the big one is KL. Like the big one, the question is asking for you. So I think for now, I see two shapes, two squares. Definitely they are similar to each other, right? The two squares are definitely similar to each other. So if I want to determine the area, I just have to find out the side ratio. This is exactly using what we said. Area ratio is actually equals to similarity, or we say the side ratios perfect square, right? So that being said, we can put it, the area of the green one, area of the red one equals to two side, right? Side green, side red, perfect square. The question already gave you, this is 99. This is what you want to choose, what you want to search, calculate. As long as you figure out the side ratio, our work is done. Okay, so the $1 million question is, how can I find out the side ratio between these two squares? Something like maybe ML over GH, like whatever. I just want to give an example, right? Maybe this guy over this guy, whatever. Maybe this guy, maybe another guy. I don't really care, right? I just want to ask you, what is the relationship between those two? And then that's it. Okay. So now let's get onto it. Let's try to figure out how we're going to find out the relationship. Well, the only condition the question gives me is actually E is a midpoint, right? If E is a midpoint, let me say this. So this blue triangle, ED in this blue right triangle, ED over DC is actually 1 over 2, right? This is 1, this is 2, right? I think this is understandable, okay? If that's the case, I can actually declare all the right triangles in the diagram. They are having a 1 over 2 similarity ratio, right? Does it make sense? Because all the right triangles, they're similar to each other. Is it right? You see, this angle is the same as this angle, is the same as this angle, same as this. All the right angles, they're similar to each other. So if the one blue right triangle has a 1 to 2 like similarity ratio, every other things are exactly the same. Right? I think this is understandable, right? This is not a magic. In that part, let me try to do a very quick analysis. If you can follow me, you will see where I come from. Okay, so first, within this little yellow triangle, this is also a 1 to 2 relationship. I'll say this is 1 and this is 2. Okay, now I go to this black triangle. This is also a 1 to 2 relationship. If the first one is, this is 2, this is going to be 4, right? Make sense? These are all similar to each other, all 1 to 2 relationship. And then let me come to here. This triangle, this black triangle is actually congruent to the previous black triangle. Does it make sense? They're all black two right triangles. They're the hypotenuse, they're like those two hypotenuse are the two sides of my red square. Of course, they're the same. So these two triangles are congruent to each other. If they are congruent to each other, this is 4, this is 4, this is 2. Right? This is quite understandable. Okay, if that's the case, let's think about it. This is like a square, right? So the side length is 4 plus 1 plus 2. So the side length is actually 7. So that being said, this part is also 7. Right? But you are telling me the HB is 4. So that being said, this part is going to be 3. Because adding them together, you have to get 7. All right. With all those information, you know what? I find something very interesting. Let's check it out. Can you look at these two shapes? The diamond shape for the green one and diamond shape for the black one. The diamond green, use color here. Diamond green and your diamond black. They are actually H, B, C, G. The green will give a name A, M, L, H. These two guys are actually similar to each other, right? Those two diamond shapes, they're actually similar to each other. If they're similar to each other, I can say, I'll take one side, ML over HG. Use the color. ML is here. HG is here. They will be equals to what? AG over BC, right? AG is here. AH, sorry. AH. AH over BC. AH is here. I'm going to use the color here. AH over BC, right? Because they are corresponding size. Two shapes, they're similar to each other. The corresponding size will be proportional. AH what? H is you just calculate 3. BC is the side length of the big square. This is 3 over 7. AH over BC equals to 3 over 7, aka ML over HG is 3 over 7. What is ML over HG? It's like a deja vu. It is here. ML and HG, I'm going to use that different color. Maybe here, ML, HG, they are exactly the two sizes of the green square and the red square. So this is 3 over 7. So that being said, the green square over the red square equals to 3 over 7 perfect square. Is that right? And this guy you're telling me is 99. So quick calculation, the red will be 539. 539. So that's it. That's exactly what the question is asking for you. Right? 539. So that being said, as long as you can use the similarities ratio, perfect square equals to the area ratio, you solve this problem fairly quick. You see, in this entire problem, there's no heavy calculation, complicated calculation here or there. You just do some very easy peasy similarity thing, and then you do some angle, side chasing, right? Not angle chasing, side chasing, and then you get this relationship. It's like so easy. So trust me, the similarity issues perfect square equals to the area ratio is extremely important. They keep asking this from time to time. So especially in some relatively difficult problems, they're gonna really ask you to do this. If you know how to do this, it's really gonna help you to expedite your calculation process significantly. Try to do this. Okay? In today's homework, I'm gonna give you another example, another question, exactly the same thing. If you understand the similarity ratio, you'll be able to solve it fairly quick. No problem at all. So far, so good? I think for the second category, I don't want to say too much. It's the similarities property, right? You just know how to determine two shapes that are similar to each other, how to use the similarities ratio. You'll pretty much solve all the problems fairly quick. All right, if all good, let's go to our third category. In the third category, I'm going to say how to remember and use some special angles trigonometry. Like I said, right? Previously, you know how to do how to do 30, your day school 30, 45, 60, 90. These are basic stuff. You have to know it. This is easy peasy. And on top of that, in my lecture, I always ask my student to remember the following as an extra. Okay? These are the angles I want you to remember from 15, 18, 36, 54, 72, 75. You need to remember the sine, the cosine. Tangent is okay. You use sine over cosine, you get tangent, right? You know, at the first sight, most of the students say, oh, no, I can't remember that too much. But you know what? Let me try to give you a little bit idea. You can actually reduce, and you can reduce the calculation significantly. So first, you know the core function. Sine theta equals to cosine 90 degrees minus theta, right? So that being said, as long as you know everything, I'm going to remove this, okay? So let's say as long as you know 15 degrees, 15 sine will be the same as 75 cosine. 15 cosine will be the same as 75 sine. So that being said, as long as you know 15 degrees, you no need to remember 75 degrees. Do you guys follow me? So let me have a quick touch base. Yeah, let me have a quick sync up. Are you guys all follow me? So what I'm saying, do you guys follow me? 75 degrees and 15 degrees, they are adding together equals to 90 degrees. So as long as you know one, there's no need to know the other. In our regular lectures, we keep talking this. This is very important. Same thing applies for you guys. So as long as I know 18 degrees, 18 as what? 72. They are the same thing. So no need to remember 72. As long as I know 36 degrees, there's no need to do 54, right? They're all the same thing. All good? Okay. Actually, you just have to focus on the first 3 rows. First 3 rows. And also, like I keep telling you, you don't really have to remember tangent if you can't, because tangent equals to sine over cosine. So therefore, if you feel lazy, you can forget about the tangent, just to remember sine and cosine. And one more thing is, this is more like for our students. I think you can remember where I come from. 36 degrees and 18 degrees, you can using the double angle formula. Is it right? Sine 36 degrees equals to 2 sine 18 degrees and cosine 18 degrees. So that being said, you do not have to remember sine 36 degrees neither. And the cosine 36 degrees equals to cosine 18 degrees square minus sine squared 18 degrees, right? So as long as you remember 18 degrees, you do not have to remember this 36 degrees neither. So I'm like, simplify everything. That's actually everything that you indeed need to remember. Only these four. Okay. The other students, if you do not understand, it doesn't matter because old students, they know we already talk about the double angle formula, the like half angle formula. If you're not familiar with this, it doesn't matter. We cover that in our regular lectures, and like the AMC definitely test you for that. So you need to do some preparations by yourself to figure out how to follow this double angle formula thing. And but that's like the basic requirements for the AMC. So what I'm trying to say is that if you really remember everything that we talk about, you just have to remember these two, 15 degrees and 18 degrees. As long as you know these two, you will be able to easily elaborate a lot of 16, I mean like 36, 54, 72, 75, so on and so forth. Trust me, this is very important to remember the accurate value, not the one you calculate, the accurate value for those guys, because sometimes that's going to help you really to expedite your calculation process. Okay, let's go for some maybe two real examples that you will understand where I come from. Okay, let's go for two examples. You can find out if you know how to do this, you're going to significantly save your time. There you go. The first problem we're looking at is a problem that comes from 2014, AMC10A, question number 22. The problem says in a rectangle ABCD, ABCD, I'm just gonna write it here, ABCD, AB equals to 20, BC equals to 10. Let E be a point and a point on the side CD such that CBE equals to 15 degrees. This guy equals to 15 degrees. So the question asks you, what is the measurement for AE? What is the measurement for AE? This problem, if you do not use our trigonometry, certain angles trigonometry, you're going to do a lot of calculation. This is question number 22. They won't let you go if you just do some very easy peasy calculation. But trust me, using our way, you're going to find out there's something so easy. So that being said, what are you going to do? This is super straightforward. If you want to determine the value for AE, let's just focus on this first. What's the value for EC? EC is actually 10 times tangent 15 degrees, right? EC is 10 times tangent 15 degrees. Tangent 15 degrees is 2 minus root 3. So this guy is 20 minus 10 root 3. Because the total value AB is the same as CD as 20. So this guy is 10 root 3. This guy is 10 root 3. Let's go to this right triangle using some Pythagorean. Solve the problem in 2 seconds. This is 10. This is 10. And this is 10 root 3. And the hypotenuse is what? It's 20. So AE equals to 20. That's it. QED. That's it. You see? If you remember some special angles trigonometry value, it's going to significantly expedite your calculation process. Nothing you need to calculate too much, right? If you check the official solution of like a LPS, like the regular solution will take long way. But here, so easy. That's it. This is question number 22. All good? If all good, let's go for another problem. This problem is the one I just mentioned. It was the problem for question for AMC10 and AMC12 together, both question number 25. This is a challenging problem, but trust me, using my way, you use maybe like 1 minute, 2 minutes maximum, you can solve the problem. Rather than 20 minutes waiting time for sure. This is the last year's problem, 2023. This is AMC10B and also AMC12B, question number 25. Okay, so what does the question say? The question says, you have a regular pentagon. Okay, so this time is the question that's not giving you hexagon, it's pentagon. With the area √5 + 1, is printed on the paper and cut out. 5 vertices of the pentagons are folded into the center of the pentagon, creating a smaller pentagon. You basically unfold 3 vertices, and then what is the area of the new pentagon? I'm going to give you the shape first, like the graph. This is important for you to understand, right? So let's say you have this pentagon and A, B, C, D, all of this, and then you have to fold, right? Fold all those 5 vertices together to create a new pentagon. So this is more like what? This is more like you're folding, this kind of like a folding trace. You fold from the dashed line, fold from the dashed line. Whenever everything's ready, your small pentagon is actually the one in the middle. Which makes sense, right? This is not a magic, right? Yeah. You just basically fold. Because I'm gonna give it here. This is your small pentagon after you fold it. Fold means what? I'll give an example. Let's say you have this side A, you have this vertices A, it's gonna be O, all the way go to this O, right? Same thing B, C, E, like whatever, right? This is not a rocket science, you should understand. So with all those information, the question asks you, what is the area ratio between the small, so the question is asking you, yeah, what is the area of the small pentagon? Again, I think just use whatever we just introduced. The regular pentagons, they will be similar to each other, right? So therefore, the small pentagon over the big pentagon will be the similarity ratio's perfect square, right? Side big, side small. Side big, side small. Okay. How can we figure out what is the side big, side small, right? You know, as long as 2 shapes, they're similar to each other, the corresponding sizes, they're like the ratio is always the similarity, right? It does not have to be the side or have to be, you know, like a certain thing, right? As long as the same, let's say, if I want to say that, give me an example, 2 triangles, if they're similar to each other, 2 angle bisectors, right? The corresponding angle bisectors, the ratio will be the same. Is that right? Corresponding angle bisectors with the same ratio. So this time I'm going to ask you to do something like this. Let me try to find out this. This is actually the height of my small, pentagon, right? And this is actually the height of my big pentagon. So what I'm trying to say, if I use ON perfect square, this is also going to work. Do you guys follow me? Can I have some feedbacks? Are we all good? Yes or no? Yes or no? The 2 sides, OM and ON, these 2 sides are definitely the same thing. It's going to give you the same thing in terms of the, you know, similarity, blah, blah, blah. So let's try to figure out what are the ratio between OM and ON. For OM, I'm not worried about too much. OM is 1/2 of OA, right? Because this is a folding, right? The dashed line is actually folding. I said A will be superpositioning to O. So definitely OM is going to be the same as OA. So OM is going to be the half of OA. Then what about ON? ON will be OA times sine angle OAE. Is it right? I use the color maybe blue. ON will be OA times sine OAE. So OA will be cancelled. So this is going to be 1/2 sine OAE, perfect square. Is that right? What is sine OAE? Sine OAE is half of this interior angle. Half of this interior angle, right? OAE is 1/2 of angle A, I'll say angle A. But this is what? This is a pentagon, regular pentagon. How can you determine the area? Do you still remember how can you determine the interior angle? 5 minus 2 times 180 divided by 5. This is what we introduced in our very beginning, right? So that being said, this is 54 degrees. Angle A is 180. I'm sorry, 108. And my OAE is actually 54 degrees. So that's 1/4 sine square, 54 degrees. Sine 54 degrees, we just told you, right? Sine 54 degrees is actually here. Sine 54 degrees is here. √5 plus 1 divided by 4. So you plug in the value to here. And the smaller, what is the size of the smaller one? Okay, this is a regular. This is √5 plus 1. So now you have S small √5 plus 1 equals to 1, 4 times perfect square. You solve this, you get your value for your new small, which is, yeah, I don't really have the number. I don't really have the final answers here, but you just basically calculate it, you get what you need. That's it. You see, this is question number 25, even for AMC 12. And you use my solution only, I think, 2 minutes maximum. You get what you need. You just have to remember. The only thing I ask you to remember is some special angles trigonometry value. Do not go for too complicated. If you check the AOPS, they have the regular solution. Oh my God, it's going to take pages. Many auxiliary lines here and there. But using my solution, easy peasy. Are we all good? So far, so good? Any questions? So far, so good? Okay. If all good, let's go to our last category. The last category is more like some circles, some tangents, circle, tangents, whatever. These kind of things. As long as you see circle, see tangent, you're going to use all of this. Also, I'm going to give you an example. I also want to give you some very number 4. Yes. There you go. That's a question. So this is a problem also from 2023, AMC10A, question number 22. So the problem says you have 2 circles, C1 and C2. Each of them, they have a radius 1. Okay, each of them have a radius 1. And the distance between their, okay, I'm going to highlight this, right? All the important thing I want to highlight. And the distance between their circle centers 1/2. Okay, you see? This is here. You have 2, right? And this guy has a 1. This guy has 1. And this is 1 or 2. And Circle 3 is the largest circle internally tangent to both C1 and C2. So you see this guy is actually tangent to C1 and C2 internally. And circle 4 is both tangent to C1, C2, and C3. Okay, you find another one on the top. So with all those information, the question asks you to determine what is the radius of C4. What is the radius of C4? You know what? As long like last year, like students really asked me for this question. I have no idea. I got so, I'm kind of like freaking out because there are so many circles here and there. I totally have no idea what to do. But I told him that you shouldn't, because we have already teach you the strategies, the conditional react. As long as you see circles, right, they're tangent to each other, what are you gonna do? You still remember? We just mentioned, as long as you see a bunch of circles tangent to each other, what are you gonna do? These are the conditional react. You have to follow those conditional react, and you'll be able to solve your problem very quick. The condition react is do the connection between the circle centers. Still remember? I'm gonna put this graph here. It'll be easier for us to do all the calculations, right? I want to give you some example. Let's say we have the circle centers, right? So I'm gonna put it here. I'm gonna first highlight all the circle centers. This is maybe A, and this is maybe B, right? Two circles. And like this is O, because you see you have the C3. C3 is actually using the symmetric property, right? C3 is actually using O with the circle center. And what about this? This is maybe, I'm gonna give you a number, maybe, I don't know, maybe E, okay? You have everything, right? Now you just have the connection, right? As long as you see any circle problems, do the connection between the circle centers. I'm gonna use the color maybe black, okay? Because these two, the C4 and C3, they are tangent to each other through connection. The C4 and C1, they are tangent to each other through connection. At least I need to basically finish all those connections, right? That's going to help you to solve all the problems. Now, let's have some quick number crunching. We'll see what's going to happen. So in that part, I'm going to maybe try to extend it like a little bit. Use the color maybe red. This is R, right? Okay. This is R. This is R. I'm going to extend it like a little bit. This is also R, right? R. That's everything that we need to know. And let's have a look at it, okay? I want to figure out the value for R, right? So I most likely want to find an equation. Equation of R, and then solve R. Where can I try to find out equation? I think the very straightforward way that you can see is you have a triangle here, right? This triangle is actually very conspicuous. This is a right triangle. Let me try to have a look at it. So let me see what's going to happen for this right triangle. Hopefully, I can find some values and then solve the values thereafter. So for my right triangle, the hypotenuse is actually my C1's radius minus C4's radius. So this is 1 minus R. Is that right? 1 minus R. And then because this guy is 1 over 2, using all the symmetric property, this is 1 over 4. Right? This is 1 over 4. If this is 1 over 4, let's have a quick look at it. If I can figure out the value for this guy, my work is done, right? So I'm going to be able to use the Pythagorean and solve all the problems. Okay? I'm going to use the Pythagorean to solve all the problems. How can I deal with how can I figure out the value for this yellow one? Let's have a quick look at it. So I'm going to try to maybe do a quick connection, extension here. Let's say T. Of course, I know AT equals to 1, right? Because AT is actually the C1's radius. What about AB? AB is actually 1 over 2, right? So with those, all those information, BT is 1 over 2, right? This is 1 over 2, which makes sense. AB is 1 over 2, and BT is 1 over 2. If BT is 1 over 2, OT, O is here, don't forget. OT is actually what? It's 1 over 2 plus 1 over 4, because this is 1 over 4, right? OT is going to be 3 over 4. If OT is 3 over 4, so OE, excuse me. This is E, right? E. Because OT is the same as OE. So therefore, oh, sorry. Oh, sorry about that. This AM is here. OM, sorry. OM, yes. Like my note have a problem. Yeah. OM is actually the same as OT equals to 3 over 4. So this part is 3 over 4, right? I'm going to use the color green. The green part is 3 over 4. Then what about OE? OE will be OM plus R. 3 over 4 plus R, right? This is R, little R here. So the OE, if I drag it out, O, M, E, A. Okay, this guy is 1 over R, 1 minus R. This guy is 3 over 4. This guy's R. This guy is 1 over 4. So you would definitely use the Pythagorean theorem in this part, and you can find out an equation. The equation was what? 1 over R perfect square is the hypotenuse equals to 1 over 4 perfect square, AO, plus R plus 4 over 3 over 4 perfect square. Right? This is the relationship, the Pythagorean relationship between the three sizes within this triangle. Solving this very quickly, you get R will be equals to 3 over 28. Do we have it? 3 over 28. You see, this is question number 22, but there's not something so complicated, right? As long as you figure out this, you'll be able to find it something so easy. Does it make sense? So that being said, as you can see, this is actually a very easy peasy process to solve this triangle, area, kind of like tangent problems, as long as you follow what we're talking about. We always want to make sure that you follow our strategies, our conditional react, do the connection, basically find out all those numbers, and then you'll be able to get it out, right? So this is actually something very important. I really want you guys to remember. We try to give you guys more interesting categories, but our lectures is very limited. Our regular lectures actually have so many problems, so many concepts I can show you. I can flood it to you, flash you. But for this bootcamp lectures, we only have a very limited bandwidth. Hopefully this is give you a big direction. What are you going to do? Okay, I think generally speaking, this is our lecture number 1. Our lecture number 1 is actually give you a big directions how to do our, the 2D geometries. We start with the basic concepts, go to the most important type of problems, and then give you the real problems. We might give you some difficult problems, but always focus on the last 4 or 5 problems, which is, I think, more important. And this lecture will be working with our crash course lecture. our crash course lectures, always question number, maybe number 10, number 13, always to number 20, that you can do more practice. I'm going to help you to solve it, give you some explanations there. So these two lectures working together is going to really help you to cover all the problems from 10 to 25. For first 10 problems, they're easy peasy, you do it by yourselves. So that's going to be a very good coverage about all the lectures. So hopefully you enjoyed today's lecture. And if you want to have some free lectures, you can scan this barcode. This is actually our WeChat barcode. Do a scan. Our customer service is going to be able to send you 100 hours free lectures. And today's lecture also comes with a homework. I'm going to upload it into our Google Classroom. You have 1 week to finish the Google Classroom homework. I'm going to grade it, and then we can take it from there. All right. So any questions? Okay, I see some students here. Questions? Yes, so basically that's what we want to say for today's lecture. Hopefully you enjoyed today's lecture and you enjoyed the lecture as well. And I'll see you guys for the next week. If you want to what's code for the classroom, you can scan this barcode. You need to register. And then we'll be able to send you all the classroom, everything. Yeah, if you do not have it, if you register, you do not have it, you can talk to me and we'll be able to send you the information. All right, perfect. Take a screenshot of the WeChat barcode and then our lecture is going to wrap up. Thank you guys. Bye. Have a good one.